Okay, welcome, ladies and gentlemen, boys and girls of all ages, to Russell's Rata Swap review. I'm your host, Russell Harvey, CTO at RDX Works, and let's play our game. Today we are going to go over an implementation in Scrypto of Uniswap V2, which we call Radiswap. We'll explain how it works, and then I will go through the same code in Solidity in the actual Uniswap V2 implementation, and you can be entertained as I struggle through it and try to translate what it is that I'm reading. Quick orientation for anybody who is unfamiliar with Uniswap. Super condensed explanation is that it allows anybody to create a trading pool between an arbitrary pair of tokens. And there is a clever little algorithm that maintains that the amount of token A in the pool times the amount of token B in the pool always comes out to some constant product. And so what this means is that anytime somebody wants to put in token A into the pool and get out token B, the price of B against A in that pool goes up, and vice versa. If people are pushing token B into the pool trying to swap for token A, then the price of token A against B goes up. And the reason people would want to add liquidity to these pools is that if you do so, if you add A and B tokens to the pool in the correct ratio, such that you are providing more liquidity so that people have a larger supply to trade from, the pool will mint you what are called LP tokens, liquidity provider tokens, which entitle you to a share of the A and B tokens in the pool. And moreover, every single time that someone does a swap in the pool, whatever token you're putting into the pool, a small amount of that is deducted as a fee that goes into the pool. And so the hope is that as a liquidity provider, that at some later point, you can turn in your LP tokens to claim your correct share of A's and B's in the pool, and that those the value of the A and B that you're pulling out down the line is greater than the value of the A and B you put in initially. So let's start with the Radix side of things. Let's go to the Radiswap implementation. And like all blueprints in Scrypto, we have things divided into two sections. There's the Radiswap struct, where we define what are what's the state that we're going to maintain and manipulate. And then there's the actual implementation, which defines all the methods and functions that are going to manage that state. So in our particular case here, let's start with actually the two most important things. We're going to have two vaults, the A pool and the B pool, and this will be our supply of token A and token B that we are going to be managing, that we'll make available for swapping on our consumers. We're also going to need to maintain a record of what is the resource definition of our LP token so we can recognize it when we see it. And we have a vault here that contains a little authority badge, and this is the authority that lets us mint or burn LP tokens at will. These other bits here on the fee and the LP per asset ratio, these are just basically things to make the algorithm function correctly on managing the correct ratio between the two assets, and I won't get into them. Let's go into the actual implementation, and I will go over fairly quickly how we create a new Radiswap pool, largely because most of the interesting work is actually done in the portions where we're doing swapping and adding liquidity and removing liquidity, but I will go over this stuff briefly. Essentially, the user has to, in order to create a new pool, they have to pass in a supply of A and B tokens. They have to tell us how many LP tokens do you want to represent the 100% share of the pool, which is what you're starting with when you're the only person who puts in. This number is pretty much arbitrary. And then we have the user pass in a few pieces of information to help the LP token be friendlier on the ledger, so that if somebody sees it, they could see, for example, what pool it belongs to and the name of it and that sort of thing. And then the user specifies a certain fee, which again I won't get into as it's just part of the needed for the algorithm to collect our correct amount every time there's a swap. We are going to do some basic checks up front. We'll make sure that the user is not passing us in empty buckets for A or B, because that would get us into a place where it would be impossible to set up a correct ratio between A and B if one is empty. We're going to make sure that their fee falls within the valid range. And then we're going to do a little bit of minting. First, we are going to create our badge that's going to have the authority to let us mint or burn more LP tokens. And then we're going to make our LP token itself. This is going to be a fungible token, and it's going to be both mintable and burnable. That it's which you can think of usually here as a mutable supply token. And the badge that's authorized to alter that supply is the one we just created, this LP mint badge. That's what this argument here is. And we'll actually create that with no initial supply on this first call. And the first thing we're going to do is to mint our initial supply based on how much you told us represents 100% of the pool. Once you have that, we get to this bit for the algorithm of making sure that we are maintaining what is the constant product that we're expecting to maintain over time. And then we will make our Rata Swap component, which consists of the resource definition of the LP token we just made, the badge which is used to mint or burn LP, our A pool and our B pool, which is our supply of funds, and the fee and the asset ratio that we just need to remember for future operations. Once we've done that, we will return to the caller the component we just created and whatever bucket of LP tokens that we made on their behalf. We'll go into one more. Let's go into swap before I dive into Solidity. Let's go down to our swap function, which is far and away the most common way to interact with the component. So when you perform a swap, what you're doing is you are, regardless of whether it's A or B that you want, you are giving to the swap function one of the two, and we will give you back the correct amount of the other one, less the fee for performing this transaction on your behalf. So the first thing we're going to do is we find out what is the fee that we need to charge. Again, this goes to how the algorithm works. We won't get into that. And then we're going to find out, okay, what did you give us? Did you give us the A token or did you give us the B token? Because we know we want to give you the other one. So if they've given us our input tokens is the same as the A pool resource definition. They gave us A tokens. We're going to say, okay, we're going to give you some amount of B. And what that's going to be is basically there's a little bit of math here that says how much do we have? We're just looking directly at the pool that's in our hands and saying what's there. And then what does the math tell us is the correct amount based on how much A you have given us to make the constant product remain the same. And that calculates out to B amount. And then all we have to do is we take our A pool, we put in the tokens you gave us, and then from our B pool, we take out the appropriate amount. We'll now skip this second half, which does the exact same thing in the case that the user gave us B instead of A. And then we're going to have, due to the way the fees work, we're now going to have a slight change in what that asset ratio is, because again, we kept some as a charge for operating this service. And then we're going to return the output tokens, whatever we took from the pool, back to the caller. And that's it. So in the case of a swap, you just give us as much A or B as you want to swap. And then on the other side, you will get out whatever the algorithm calculates was the appropriate amount. In the event that you wanted to have a guarantee for yourself, like for example, at this time, I think that for giving 10 A's, I'm going to get about 50 B's. But when I submit this transaction, someone else might come in front of me, and then maybe they're going to put in a bunch of A's and get out a bunch of B, and they're going to raise the price of B, and so I won't be getting 50 anymore. And to guard against the amount that you're getting back being wildly outside your expectations, in the Radix transaction model, you can actually set that as just part of the transaction as a guard that, hey, at the end of this whole thing, for example, if I was expecting to get 50 B out, I might say if it's if the amount returned by swap is less than 49B, then abort the whole thing. I don't want to do it. And that bit of logic is not something that the Radiswap blueprint developer has to put in their code. You get this for free with the transaction model. The person who's building, for example, the UI layer on top, the web page you're going to interact with to do this, could put in that logic for you, and also put in the ability for the user to hand set those guardrails as they will. So let's go over to how this looks in Solidity, and you will have to bear with me as I am not a Solidity developer. I've gone through a quick run through to try to familiarize myself with how this works. I'm going to actually skip past the part where you do pool creation, because it behaves a little bit differently than how we do it in the Radix side, and that basically you have a contract that is a factory contract that creates the correct pair for you, and it functions similarly to how the blueprint performs that function for you on the Radix side, where you just specify the parameters you want, and the blueprint then instantiates a component from it. And I'd actually like to jump just straight into the meat of how we would do a swap on this. So Uniswap V2, there's a couple of different sets of contracts. There are the periphery contracts, which are the things that a user is expected to actually interact with, and then there is the set of core contracts that actually do heavy lifting underneath. And the periphery basically does things to combine certain calls to the core contracts to make them atomic, so they execute all together or not at all, and to do some safety checks. So let's get into how would we do a swap on this router periphery contract. And you'll see there's a couple of them. Let's look for some swap logic. Here's remove liquidity, or more remove liquidity. And you'll see we have this little private swap, which has other ones in front of it. There's swap exact tokens for tokens. There's swap tokens for exact tokens. There's swap exact ETH for tokens. There's swap tokens for exact ETH. And the reason you have all these different external methods is, one, is that Ether does not behave like an ERC20 contract does. So the calls you have to use when you're doing ETH as opposed to an ERC20 contract are different, and so they have to have different logic to handle that. And then also we have this ability to set guardrails, which is intrinsic in the Radix transaction model, is actually something that the contract developer has to think about here on Ethereum, where they want to allow for this notion of I want exactly the following trade to happen, or I'm going to be okay with getting, if I give you 10A, you give me the amount of B that you give me, that sort of thing. And all these things work to achieve that underneath the hood. So let's just pick exact tokens for tokens, as this is top one. The inputs are basically what you expect. We have how much are you giving me? What's the minimum amount you will take on the output? Some kind of call data here that I'm not sure what it is. And then we have an address that you're going to be sending to, and a deadline, which I suppose is how long we're allowing for this to happen. So we'll start with amounts equals Uniswap V2 library get amounts out. I think this is basically to try to figure out based on the amount you're putting in, that you'd be getting a correct amount out. Let me look at V2 library. Out. Right, okay, yeah, so this is just making sure that we have we're doing our bit of math and finding out that we have calculated a correct amount to give out to the user. And we're going to make sure that it is above some minimum threshold, and then we're going to do transfer helper safe transfer from. Basically going to look up what is the Uniswap pair. We have a thing that manages what all these pairs are. And we are going to actually send your input tokens at this point. Transfer helper, I believe, is in their main library. Yes, transfer helper. Okay. So transfer helper safe transfer from. Okay, so what we're doing here is we are essentially, this is making a call to whatever the appropriate method and address is. And interesting note on how ERC20 functions, that when you call for a transfer, while it returns a Boolean which indicates whether it was successful or not, it is valid for an ERC20 token to, or a contract to return a success result, as in it's true, but then to have a data payload that comes back that if you decode it, and that decodes into a false Boolean, that means that it actually failed. So this little helper here, safe transfer from, is just to make sure that we are aware if the transfer actually failed. The fact that this is necessary is a little crazy to me. I mean, transfers are, of course, the heart and soul of what has made Ethereum successful, and the fact that you need to have a function to make sure you're doing it safely, and in this case, this is only one that handles it for ERC20. This has nothing to do with ETH, which works a different way. Is a little bit concerning to me. It's like you buy an airplane ticket, and then at the seating chart, you can pick from a seat, or for $20 extra, you can get a safe seat. I prefer just to fly the one that all the seats are safe. So let's go back to the router and get into the actual meat of this. So at this point, we have sent our tokens in to whatever the correct contract is. And now we're going to do our swap, which now uses this little internal function, which is going to get the input and output addresses, sort tokens. Okay, so sort tokens is going to put them in a predictable order and make sure that you didn't give us the same thing of token A and B, and you didn't give us address 0. Important for their validation. And basically this little array, we're going to get out the correct value for what is the amount out, and figure out what our to address is. And then we're going to actually go to the pair contract, which is a core contract, by looking it up with the factory saying, hey, do you have one of these? And then I'm going to call swap on that contract. So let's go into that. That is core. There we go, V2 pair. Okay, and let's look for swap here, which is what we're going to call. It's minting, and here we go, swap. Okay, so now this is a publicly callable function. There's a little warning here that you shouldn't do it without doing your external checks, and in this case, it's going to expect that money has already been transferred in. And I see we have this lock. Let's find lock. Okay, so it looks like this is functioning. Okay, this is to prevent reentrancy. So this is, you basically have a little mutex here that, because on Ethereum, when you are doing a, for example, a send to an ERC20 contract, you're just calling a method that they've defined. And if someone wanted to mess with you within that method, it could itself then, when you think you're just doing a send, it might do a call to Uniswap, and now it could re-enter the logic path you're in already, and it might be able to pretend it has more tokens than it should, or other weird and hard to reason about reentrancy problems. So basically all this is doing is saying, I'm going to make sure that I can't be re-entered once I start this. I believe in Solidity this is recall your same function. So lock it, do my call now that I've got the lock, and then unlock it. And sorry if I got that incorrect for any Solidity experts. Okay, back to swap. So now we've successfully gotten into the function. We have the mutex and we're rolling. We will now make sure that the amount out of one of the tokens, at least one, is greater than 0. Otherwise, it makes no sense to do anything. And we're now going to set reserves, should be the amount we think we have of each one. Get reserves. The reason for this is they're doing some clever bits to use 112 to, yeah, so this lets them fit in a single 256-bit integer. They can use the high amount for a high 112 for reserve 0, the next 112 for reserve 1, and then the last 32 for this block timestamp that they're tracking. So this is just a clever way to save a bit of gas on storage. So, okay, moving on from that. We now have what we believe to be our reserves. We're going to make sure that we aren't going to attempt to give away more than we possess, because if that happens, then we don't have enough liquidity to fulfill this request. That makes sense. And now we're going to get a couple of local variables for balances, 0 and 1, and token addresses. Wire 2. So, okay, so this is we're making sure that our 2 address is not the actual token 0 address, and same thing, it's not the actual token 1 address. This is making sure that the user doesn't make a careless error and give you the ERC20 contract address, not only of the token that they're sending it in, but of the destination, basically be like sending the token to itself. That's certainly going to be an inadvertent user error, and so that's what this is trapping for. Just to point out, in the case on the Radix side, that'd be impossible because, again, we don't actually do the transfer. We leave it for our caller to figure that out. So if you want to do a swap, we'll just give you the amount of tokens out and you do what you want with it. Here we're going to do safe transfer, which I assume is the same. Yep, this behind Cobra selector. This is probably just the, yeah, okay, so this bit that they're doing right here is to just avoid importing an interface. They're saying, I know it's got a transfer function because it's an ERC20, so I'm shortcutting to that. I'll do the call and I'll make sure that same logic I talked about before, that I have to get a successful result, and I have to make sure that there wasn't this little payload indicating that there was an error, even though it said it was a successful result, else I fail. So we're just going to go ahead and send at this point, optimistically transfer tokens, and I guess we'll later figure out if we shouldn't be doing that and abort the whole thing. Not exactly sure what this part is doing. Gonna have to skip past that. And balance 0, which we declared up here in balance 1, ERC20 is probably ERC, yeah, okay. So what we're doing here is we're saying, okay, important distinction between Rata Swap and how it works on Solidity is the Uniswap pool itself, the contract, this V2 pair contract, is not, you're not directly seeing the balances. You have an address, and that ERC20, say you have address 1234 for token A, and that's an ERC20 contract, and token B is address 5678. Your balance, you have to go interrogate that contract to say, hey, what's the balance of my balance, my address right here? So this is saying, okay, I had a cached value that I believe was correct of these reserves, but I'm not certain that they are still correct. And the reason they may not be correct is that while I might ensure that on my own side in my Uniswap contract, I am never sending out my balances of things unless they were done in a swap or a liquidity burn. But what I can't guarantee against is that what if somebody just sent in tokens to my address on that contract? That, I mean, the way the constant product is maintained, I can't have people manipulating those balances without me being aware of it, because basically you've now changed the effective price without actually participating in the correct process to do so. So I actually don't know how they... Nope, never mind. I'm now answering my question. Just read this to see if this is accurate. I think what this is doing here is basically resolving exactly what I just said, which is in the event that my balances have gotten incorrect by somebody depositing more money, which they shouldn't do, but who knows why it occurred. Anybody can come in and call this skim function with their address, and it's going to say, okay, let me go look at my balances and see if they match what I expect, and basically whatever the balance of, subtract my reserve. Like, what's the difference? I don't want it. Just give it to whatever Good Samaritan came in and called the skim function. So that achieves the goal of then you would get back to your correct constant product. So clever, but just a tough side effect of this fact that you don't actually control your pool yourself. All you have is you have this little silo that's maintaining a balance sheet, and you're one of the balances on that sheet, and so you have to go interrogate it to say, hey, is my balance still what I expect? So after we've done that, we're going to do a bit of math to make sure that we figure out how much we're supposed to be sending. Or we did already, rather. We're making sure that after we did the optimistic transfer, that we didn't get into a state where it seems that we shouldn't have done that. So that's what this, I believe that's what this math is checking here. And then I'm going to call this update function. So this is making sure if we overflowed, the effect of that is that the number would appear to be negative. And so that's just a quick check on that to make sure that by accepting the input tokens, we didn't put either one of our balances in a state where the number would not be too large for us to correctly handle. We'll exit if that's the case. And some logic here looking at, basically we can, there's this price accumulator that lets you check on average prices during a block and so forth that I'm not going to get into because I didn't fully understand their algorithm, and that's just on me as a learning thing. Okay, so we will emit an event saying that we synchronized our reserves, and we will emit an event saying that we did the following swap, and that's it for a swap. I don't know that I want to go through all that again for adding and burning liquidity, as this is actually more complex than I expected after a quick look at it. Let's look at, go back to those real quick though and see. They function basically the same way, which is, yeah, we have the same set of things where you basically have an internal add liquidity, and then you have a bunch of, or in this case just two outside, where one where you're doing two ERC20s and one where you're doing ETH in an ERC20. And the point of this is actually to make certain things atomic, in that you are sending tokens in, and then this liquidity that you're returning, this mint function. Let's go back to the pair. Let's find mint. Oh, the mint function, yeah, it only takes a 2. So what this does is this basically has to be coerced to be atomic by the periphery contract. What it does is it's going to look at what it thinks its total supply should be of the LP token, and determine that, hey, I've got an excess here and I need to basically mint enough, and I will send that to whoever you tell me to. And so of course, if you were to transfer tokens into the contract of A and B, even in the correct ratios, if you were to do that as a separate step and then call mint as a separate step, in between those two things happening, anyone could front run you on your mint. Some bot would certainly see that was a way to clean up some free money and come in and basically steal your LP tokens that you were entitled to. And that's why you should use these periphery contracts or add liquidity, where it forces that to be atomic with the rest of these things. So makes sense. And actually, when we look at router 2, last time I looked at it, I think looked identical to router 1. This bit on with permit. Presumably this is related to the fact that because you don't have, you're not directly controlling your token supply again, and so the first thing you have to do before interacting with Uniswap is actually you need to basically talk to the two ERC20 contracts that you're going to be dealing with, or if you're just putting in A for B, then just one of them. I was saying basically, hey, I get permission for this particular pair contract to basically spend my balance on my behalf. And at that point, you are trusting that not only is the contract well implemented and not malicious, but that it is not vulnerable to some kind of attack which would cause someone to be able to then steal your money at that point. And obviously that's a downside, that you are having to delegate this permission away. One of the frustrations I could see of it is that what you really would like to do is you think of, okay, if I'm about to trade in 100 token A and get some B back, I would like to tell the ERC20 contract for A, I'm only approving to send 100, and that's it, which you can do. That's part of the delegate function. The problem is that gas fees are so high that unless you are doing enormous value transfers, it's not going to be usually worth it for you to delegate authority in so much, like one chunk per trade, which would at least increase your safety at being able to have this Uniswap pair just manage your entire token supply at that address for that ERC20. And then we have some stuff for supporting fee on transfer tokens. Okay, but otherwise this looks quite similar to router 1. I'm not 100% clear on all the minutiae of why you would use one or the other. But basically, there's a lot of elbow grease here for the person implementing the web interface to figure out what's the appropriate, let me go from user intent to what is the outermost periphery function that I should be calling, set everything up, do the call, and get the user their tokens back. Yeah, let's go back to the Rata Swap side just for a moment to see how these things work on the Rata Swap side, and they should be significantly easier to understand. And let's just do, we did mint, let's do burn now, which I assume functions similarly to the converse of minting on the Solidity side if I'd gone through that. In our case, to remove liquidity, all you have to do is present some amount of LP tokens, which entitles you to a share of the pool. We will do a quick check to make sure that you've passed us a token that we recognize as our LP token, else we will say, nope, we can't give you anything for this. We will do a little bit of math to calculate what your share is. And then we will take some from our A pool, and we will take some from our B pool. And that will get us A withdrawn and B withdrawn. These are now both buckets of tokens. The LP that you gave us are now, basically, we have the share of the pool they represented has now been put in these two buckets, these A and B withdrawn buckets. We're going to destroy what you gave us using our little badge that permits us to do so. And then we're going to return the amounts. And hopefully that's a lot easier to understand than going through a periphery contract and safe transfer and all that kind of stuff. This is actually getting a lot longer than I expected, so I think I will stop there. I hope you enjoy this, and I apologize that my Solidity skills are not what they should be for getting a proper comparison of these things, but hopefully it's useful just to see that some of how the approaches are different in how you do these implementations in Solidity and how you do them in Scrypto. And with that, I will sign off. Thank you.